Welcome back, guys. Today we're going to be discussing about the Gay-Lussac's law of combining volume, the Avogadro's principle, and the Graham's law of diffusion or effusion. Okay, remember on our last class we were talking about the Charles law, the Boyle's law, and the ideal gas equation or the ideal gas law. Now, on the board here we have the Gay-Lussac's law of combining volume. Now remember from our secondary school we were taught the Gay-Lussac's law. Now what does that law state? It states that when gases react, they do so in volume which have simple whole number ratio to one another and to a volume of its product if gaseous at same temperature and pressure. Now right here we're not talking about the Gay-Lussac's law, but we're talking about strictly on the Gay-Lussac's law of combining volume. Now what does it state? It states that the volume of gaseous reactant and product of a reaction can be expressed as ratio of small integers when measured at same temperature and pressure. Now what is this law trying to talk about? Now we have a reaction here for the formation of water. Now we have H, oxygen and hydrogen to give us water. Now what are you talking about? Remember, integer are negative or positive whole numbers. What are whole numbers? Whole numbers are numbers that does not carry point, which does not have a decimal point. Now, so obviously integers are either positive or negative whole numbers. Now let's assume it's tending from infinity, negative infinity. Then let's start from -5, -4, -3, -2, -1. Then we have 0. Then let's continue from here now. We have here 1, 2, 3, 4, 5, and so on, because it tends to infinity. Now these are integers. Now what is this law trying to talk about here? It said the volume of gaseous reactant and product of a reaction can be expressed as ratio of small integers. And the ratio are in small integers. Remember, our volume can never be negative, so we're talking about here the positive integers which we have here. Now they are talking about here that the ratio of small integers. What are we talking about? So from here we have 2 volume here for hydrogen, 2 volume. We have for oxygen 1 volume, and 1 for hydrogen for water, which is 2 hydrogen, 2 volume. Now we have here 2 ratio 1 to give us 2. Now it is saying can be expressed as ratio, which is the ratio sign here, of small integers. Which are the small integers here? Now this is what this is trying to talk about. Now let's look at the formation of ammonia, the industrial formation of ammonia. Now we have here that nitrogen has 1 volume, which is 1 mole, 1 ratio. We have hydrogen having 3 volume, which is 3. Then we have ammonia to have 2, meaning 1 volume plus 3, 1 volume of nitrogen plus 3 volume of hydrogen gave us 2 mole of ammonia. Now these are simple whole number ratios. Simple whole number ratios in which a reaction can occur. Okay, we are done with Gay-Lussac's law. Let's look at Avogadro's principle. Now what is Avogadro's principle talking about? It's saying equal volume of gases at same temperature and pressure contains the same number of molecules. Now let's do some relation here. Avogadro's law said equal volume of gases contain the same number of molecules. Now let's do this relation. Equal volume of gases contains the same number of molecules, meaning volume is directly proportional to mole. Do you understand what I'm saying? Volume is directly proportional to mole. So if the volume is increasing, number of moles is increasing. If the volume is decreasing, the number of mole is decreasing. So that's what Avogadro is trying to talk about, that equal volume of gases at the same temperature and pressure contain the same number of molecules. Now, number 3 here, let's discuss about Graham's law of diffusion and effusion. First of all, when you see some questions, they will ask you to find the effusion of gas. Now, don't be confused when you see, most of the times they use the diffusion of gases, but when you see in your question, what is the effusion of the gas? Don't be confused. You are still using the same method for diffusion. That's what we are going to be using for calculations under Graham's law. Now, let's look at Graham's law. Graham's law states that the rate of diffusion of gases is inversely proportional to the square root of its density. Now, let's observe this mathematically. It said the rate is inversely proportional to a square root of the density. Now, let's make this proportionality sign to an equal to sign. So we have here rate is equal to the constant over square root of density. So let's make here a whole number on its own, which should be units. So let's cross multiply. We have arrow root d is equal to k. So from here, since we already know arrow root d is equal to a constant, therefore arrow root arrow 1 root d1 is equal to arrow 2 root d2. So now let's put arrow on the same side and put d on the same side. So what do? Let's make this arrow come this way, then this one come this way. So we're dividing here by arrow 2, dividing both sides by arrow 2. So here we'll cancel out. What do we have here? We have here that arrow 1 root d1 over arrow 2, since here has cancelled out, is equal to root d2. So remember, we are making arrow to be on one part, then the density to be on one part, on one side. So let's divide both sides by root d1. So if we are dividing both sides, let's divide here. Let's divide here by root d1. Then divide here root d1. So root d1 will cancel root d1. So what do we have left? We have here arrow 1 over arrow 2 is equal to root d1 d2 over root d1. So now it can be in this form to calculate, but let's go further. We can go further. Since we are having 2 square roots here from sorts, since we are having 2 square roots here, we can take one of the square roots, then divide the 2 densities. So the 2 density will be covered by a square root. So what am I talking about here? So let's look here. Now arrow 1 over arrow 2 is equal to a complete square root d2 over d1. Now this is the formula to calculate for Graham's law of diffusion. Okay, so now we can go further. There is also an equation under Graham's law of diffusion, which is talking about the mass of the compound, the molar mass of the compound. Okay, so now remember, density is equal to mass over volume. Now 1 liter of a gas, at 1 liter of a gas, density is equal to its mass. So now from here, since density is equal to mass, so therefore we can replace here with each other. So now we have here that R1 over R2 is equal to root M2 over M1. Now these are the two basic equations for Graham's law of diffusion. Now you can see questions. This is 1, this is 2. Now I will be solving some questions under Graham's law, which will make use of this, will also make use of this. And now there are some other formulas which I will bring out for you to build up your knowledge for understanding questions under Graham's law of diffusion, because calculations under Graham's law of diffusion are very, very tricky. So I'll be bringing out formulas which can build you on Graham's law. So there are some formulas that we don't know, which is V2C1 over V1C2 is equal to root M2 over M1. Now this is another equation under Graham's law of diffusion. Okay, so now if you don't get things or you are lost somewhere, you can go back to the beginning of the video and watch everything, then try to understand the point so you can understand when I'm teaching on the future or our next class. Alright guys, welcome to Exclusive Academy. Now we are going to be talking about compressibility factor, which is letter Z. Now this is dealing on basically ideal gases and rare gases. Remember I said on our previous video that rare gases are also called hypothetical gases, or it can also be called a perfect gas. Now we're going to be dealing on ideal gas and rare gases. Now compressibility factor. Now let's look here. For ideal gases, our compressibility factor is equal to 1 at all temperature. So if a gas is ideal, the compressibility factor is equal to 1 for all temperature. Now for rare gases, the compressibility factor is either greater than 1 or less than 1. It is not stagnant, like it's not something we can predict. Now it can either be negative or positive. So if we have greater than 1, it could be 2, 3, 4, 1.5, 4, 5, 6 as well. If it can be less than 1, it will be -1, -2, -3, -4, and so on. Now let's take a look at this note for rare gases. If the compressibility factor is greater than 1, if it is greater than 1, okay, that gas is least or less compressible than expected of an ideal gas. Now at that point, PV is not longer equal to nRT. Remember, PV can only be equal to nRT when the gas is an ideal gas. So now if this is a rare gas, so PV cannot be equal to nRT. So now PV is greater than nRT. And note that it shows positive deviation usually at high pressure. For rare gases, when the compressibility factor is greater than 1, it is less compressible than expected of an ideal gas, and PV is greater than nRT, and it shows positive deviation usually at high pressure. Now let's look at this. When the compressibility factor is less than 1, therefore it is highly compressible. It is highly compressible than expected of the ideal gas. And also know that PV now is now less than nRT. PV is now less than nRT, and it shows negative deviation usually at low pressure. So now you should get the difference between when a rare gas, its compressibility factor is greater than 1 or is less than 1, and for ideal gas the compressibility factor is always equal to 1 at all temperature. Now let's look at this other side of the board. Now this is a graph which speaks about rare gases and ideal gases under compressibility factor. Now we have here remember PV is equal to nRT. So we should say PV is equal to ZRT. So now let's make our compressibility factor to be constant, to be whole. So we have Z is equal to PV over RT. So this is what we're talking about here. So now these are gases that deviate. All these are rare gases in which we see with our naked eyes. Remember I told you that rare gases are gases we see with or we know, but for rare gases, ideal gases, it does not exist. It's just like how do I put this? It's like a standard at which all rare gases can be compared to. Now for a gas, now all these are deviating. Now for a gas to be moving at a straight line here, it shows for any gas that move on a straight line, that gas is an ideal gas. An ideal gas. So these other gases are rare gases. Okay. This should be the end of compressibility factor we're talking about. Don't forget, this is Exquisite Academy. Subscribe to our channel. Alright, welcome back guys. We're going to be talking about van der Waals equation. Now remember we have ideal equation, ideal gases equation, which we know as PV is equal to nRT for ideal gases. Now the man called van der Waals brought an equation which will work perfectly for rare gases, which brought about some correction to be made in that equation, which we have here, the van der Waals equation. Now these are the corrections he brought about: the volume correction and the pressure correction. Now this is what we have. Now P in brackets, P plus n square A over V in brackets, multiplying this V minus NB is equal to nRT. Now there are some corrections we have here. So let's assume, so this is for pressure, this is pressure, this is volume, this is volume. Now with their the way they are multiplying themselves, the same way they are multiplying themselves, but they made some corrections here, from here, then from here. Okay, let's talk about the value A here, which we don't know. Now the value A talks about the magnitude of attractive force between molecules. Okay, all right. So now the greater the value of the value A, the easier the gas is being liquefied. All right, the greater the value A, the easier the gas is being liquefied for this equation on rare gases. Now let's take a look at this other side of the board. Now the value B, which we have here, we'll discuss about this. The value B, which we have here, now this value B talks about size, talks about the size. Okay, now it is also known as co-volume or excluded volume. The value B is also known as co-volume or excluded volume. So now the greater the value of B, the larger the size, the smaller the compressible volume. Now you should take note of this. You can see this on your options. The greater the value of A, then they'll bring some options out. So just know the answer is the greater the value of A, the easier the gas is being liquefied, and then the greater the value of B, the larger the size, the smaller the compressible volume. Now this is an equation for rare gases. Now this is an equation for ideal gases. Now take note of these two equations. Okay, so now we'll be going straight to calculations under ideal gases.